Our next lesson is on percent yield. To this point, we've only looked at what's called the theoretical yield. When we do the calculations on a stoichiometric problem, we're figuring out how much product can theoretically be produced. But rarely do we get that maximum amount of product produced. The analogy is like baking cookies. You're going to have some batter that gets left in the bowl, some batter gets stuck to the spoon, and some of the batter is going to be consumed prematurely. The end result is you'll never end up with as much cookies as you theoretically could have made given your starting products. Chemists like to be able to compare the amount of product produced compared to how much could have been produced. We call this the percent yield, and you can calculate it with the following equation. This equation is actually not new to you. You've used it every single time you've calculated your percentage on a test or homework or lab. What you actually got, perhaps you got a 95 out of what you theoretically could have gotten, 100 points possible. 95 divided by 100 would be 0.95 times 100%, you got a 95%. When using stoichiometry, we can always take what we actually got over 100 grams, and that's a very easy way to convert a percentage to an amount of grams. That way we can use a percent yield value directly in our stoichiometric calculation. We'll see an example of that in a couple of slides. First off, let's visualize percent yield. I've made up an equation here. 1 pant plus 1 shirt yields 1 shirt pant outfit. We can see that here. When 4 pants, we're starting with 4 pants, and 6 shirts are reacted, 3 shirt pants outfits are produced. And they want to know what our percent yield of the reaction was. Well, first step, we have to treat it like a limiting reagent problem. How many shirt pants pairs could we make with 4 pants? Well, according to our chemical reaction, there's a 1-to-1 ratio. So with 4 pants, we should be able to make 4 shirt pant combinations. We need to do that again for our number of shirts. How many shirt pair pants can we make with 6 shirts? Again, that 1-to-1 ratio from our balanced chemical equation. We should be able to make 6 shirt pants with 6 shirts. 4 is less than 6, so we're only going to be able to make 4 shirt pair combinations. Pants are our limiting reactant. Now we go back and we look at the question in our visualization. We didn't make 4 shirt pant outfits. That was our theoretical yield. In theory, we should have been able to make 4 shirt pair outfits. But our actual yield was only 3 shirt pant outfits. For some reason, one of the pants were lost or dirty or ripped or torn, and they were not going in to making our shirt pair outfits. So divide what we actually got, which is only 3 shirt pair pants, by what we theoretically should have gotten, which is 4 shirt pair pants, then we get a 75% yield. Let's take a look at some real chemistry examples. What is the percent yield if 4.65 grams of copper is produced when 1.87 grams of aluminum reacts with an excess of copper to sulfate? As with all stoichiometric problems, this starts with a balanced chemical equation. So here we are. Aluminum reacts with copper sulfate to produce aluminum sulfate and copper. Now luckily, they told us what the excess reactant was. They say we have an excess of copper to sulfate. That must mean that our limiting reactant is aluminum. So we only have to worry about the value of that there. So let's solve for how much theoretically we can produce with 1.87 grams of aluminum. Again, we have to convert grams of aluminum into moles of aluminum. Now we can use our balanced chemical equation to go from moles of aluminum to moles of copper. And finally, from moles of copper to grams of copper, we crunch the numbers with our calculator, and we get a theoretical yield of 6.6061 grams copper. All right, again, that's our theoretical yield. In theory, we should have been able to make that much copper. How much did we actually make? We're going to look back up at the question. The question says we made 4.65 grams of copper. So we can plug that 4.65 in, divide it by the theoretical 6.6061 grams of copper, multiply it by 100%. Don't forget to carry digits and underline digits, even though they aren't significant. We don't want to round them off, or we'll end up with round-off error. We crunch the numbers. 3 significant digits here, only 3 there, despite the fact that I've carried 2 extra. I underlined them to let myself know they are not significant. That's 3 digits in both of my numbers, so my final answer should have 3 digits, 70.4% yield. Another example, if a chemist wishes to obtain 125 grams of calcium oxide from the decomposition of calcium carbonate in a real laboratory situation where the anticipated yield is 85%, what mass of calcium carbonate should the chemist keep on hand? Oftentimes we know what the percent yield of a reaction will be, as is the case here. We know that this reaction, no matter how well it's performed, is only going to give us about an 85% yield. If we want 125 grams of product, how much reactant should we start with? So we're going to be working backwards in this particular equation. Again, as always, it starts with a balanced chemical equation. Calcium carbonate is going to decompose into calcium oxide and carbon dioxide. Now we're looking for how much reactant to start with, that's calcium carbonate, if we want 125 grams of calcium oxide. Now notice I have the AY here, that's my actual yield. I want to end with an actual amount of 125 grams. That's going to help me in the next step. Do you remember I mentioned that we can turn a percentage into a mass by just assuming that the theoretical yield is 100 grams? Makes for a pretty easy percentage calculation. I actually want 85 grams of calcium oxide out of 100 grams of calcium oxide. So my theoretical yield goes on top because I want my actual yield on bottom. I know that because my actual yield is on top over here. I need the 2 to cancel out. Next, I can convert into moles of calcium oxide. And with my balanced chemical equation, I can then go to moles of calcium carbonate. And finally, with a molar mass, I can go to grams of calcium carbonate. We crunch the numbers, adjust for significant digits. We began with 3. We're going to end with 3. 262 grams of calcium carbonate would be needed in order to produce 125 grams of calcium oxide if we only have an 85% yield for the reaction.